Have you ever tried to run a massive program on your computer only to have your fans suddenly sound like a jet engine preparing for takeoff right before the whole system just completely crashes? Well, welcome to this explainer. Today we're diving into the absolute secret sauce that makes massive artificial intelligence models accessible on everyday devices. If you've ever wondered how developers are taking AI systems that normally require literal warehouses of computers to build and somehow seamlessly running them on a standard MacBook, you're in the exact right place. We're decoding a game-changing yet surprisingly simple technique called quantization.
So, let's just dive right into this by asking a very practical question. Recently, Meta released their Llama 3.1 model, and the flagship version of this AI has 405 billion parameters. Now, think of parameters as the individual neural connections or synapses in the AI's digital brain. They basically represent everything the AI has ever learned. So how do you fit a 405 billion parameter brain into a normal computer? Well, the short answer is, normally, you simply don't. An uncompressed model of this size takes up roughly 800 gigabytes of storage. That means it wouldn't even fit on the hard drives of most standard off-the-shelf laptops, let alone fit into the computer's short-term active memory, the RAM, which is what you actually need to run the program.
Uncompressed, these models are incredibly smart, sure, but they are massively heavy. To actually train that Llama 3.1 model, Meta pushed their infrastructure to the absolute limit, utilizing over 16,000 H100 GPUs. To put that into perspective, a single H100 graphics card costs tens of thousands of dollars. We are talking about hundreds of millions of dollars worth of specialized hardware housed in massive server farms, drawing enough electricity to literally power a small town, just to train and run these uncompressed models. It's a huge logistical bottleneck.
And that bottleneck brings us to Section 1. What exactly is AI quantization? We need to clearly define the primary technique used to shrink these gigantic models down to a manageable size.
At its core, AI quantization is simply the process of storing an AI model's weights using fewer bits of precision to save physical memory. The weights are really just the numerical values assigned to those billions of neural connections we mentioned a minute ago. In the digital world, precision takes up physical space on a hard drive. When we say bits of precision, we essentially mean the number of decimal places a computer uses to remember a highly specific piece of information. So if we reduce the precision of the numbers making up the AI's brain by chopping off those long trailing decimals, we drastically compress its overall memory footprint.
Quick clarification though, especially for any musicians or audio engineers out there, we are absolutely not talking about audio production or analog to digital music quantization. So if you're thinking about auto-tuning a bad vocal take or magically fixing an off-time drum beat, you can leave those concepts at the door. This is strictly about mathematical data compression inside neural networks.
Honestly, think of it like rounding a long floating point decimal to a simpler, shorter number. Imagine the number pi. You could write it out as 3.14159265 and just keep going forever. That's highly precise, but it takes a lot of mental effort to write out, remember, and calculate with. Or, you could just round it down to 3. Now, obviously, if you're calculating the exact trajectory of a rocket to Mars, rounding to 3 is a terrible idea. But if you just need a rough estimate of a circle's circumference for a high school math homework problem, 3 is close enough. That close enough mentality is exactly how AI saves so much space. Instead of storing a massive, highly specific decimal for every single connection in its brain, the AI just rounds the numbers off.
Moving right along to Section 2, shrinking models for faster speeds. Let's see how this simple rounding trick translates into massive, real-world advantages.
Rounding off these numbers unlocks some absolutely incredible benefits. First, it obviously shrinks the physical memory footprint of the model, meaning it can fit onto smaller devices. But second, because the computer's processor has fewer bits of data to crunch through, it dramatically speeds up what developers call inference. Inference is really just the technical term for the time you spend staring at a blinking cursor, waiting for the AI to generate a response. Less data to crunch means those answers just fly onto your screen. It also means significantly lower computational power consumption. And crucially, it allows these massive models to actually run on consumer GPUs. We're talking about running cutting-edge intelligence right on the gaming PC sitting in your bedroom.
Which leads us to Section 3, Bits Explained, 16, 8, and 4. To truly appreciate this compression, we need a quick look at the math behind the bits. But don't worry, we're keeping it extremely simple. Normally, AI models operate using 16-bit or even 32-bit floating point numbers. Think of a 16-bit floating point, or FP16, as a hyper-precise decimal number. It gives the AI incredible nuance, but it results in a massive model size.
By quantizing, or dropping down, to an 8-bit integer, or int8, you essentially turn that complex decimal into a much simpler whole number. Doing this literally cuts the total model size completely in half, and researchers are now regularly dropping that precision even further down to 4-bit formats, which gives you a highly compressed, incredibly lightweight model. To put the sheer scale of that reduction into perspective, consider this. A standard 32-bit floating point number has over 4 billion possible values it can represent. An 8-bit integer? It only has 256 possible values. Imagine you're taking a multiple choice test. In the first scenario, every single question has 4 billion possible answers you have to read through. In the second scenario, there are only 256 choices. You're going to finish that second test a heck of a lot faster, right? Because the 8-bit integer has such a tiny fraction of the possible choices, the processor doesn't have to work nearly as hard. The AI can perform all those complex mathematical calculations incredibly fast, simply because it has fewer options to sort through.
Let's ground this theory in reality in Section 4, Data Centers versus your laptop. Why does this optimization actually matter to you and me?
This comparison perfectly highlights a massive technological divide. With an uncompressed model, you're entirely relying on a massive data center. It's wildly expensive to run, and you have to send your personal data to a remote cloud server just to use it. But with a quantized model, you can run advanced AI tools directly on a standard laptop. It's highly accessible, and it unlocks a huge win for everyday people: total privacy. Because the model runs locally on your machine without an internet connection, your sensitive work documents, your proprietary code, or your personal journal entries never have to be transmitted to some tech giant server. Your data absolutely stays yours.
For instance, check out this real-world breakthrough. Thanks to innovations from the open-source community like Hugging Face and a technique called QLoRa, researchers proved you could squeeze a massive 40-gigabyte AI model down to fit entirely on a standard 16-gigabyte consumer GPU. 16 gigabytes of video RAM is what you find on standard gaming graphics cards you can buy right off the shelf at a store like Best Buy. Quantization takes a technology that used to require a multi-million-dollar corporate budget and puts it directly into the hands of a college student coding in their dorm room. It's a real game changer.
But of course, there's always a catch. Let's look at Section 5, the accuracy trade-off. In the world of computing, you can't get something for nothing. So let's talk about the cost.
The catch here is known as quantization error. It's the slight loss in model accuracy and smartness resulting from rounding off those high-precision weights. When you squeeze a model's brain down and round off its numbers from 4 billion possibilities down to 256, you inevitably introduce a tiny bit of mathematical noise or distortion. The neural pathways become just a little less precise. In practice, this means an uncompressed model might be able to write a perfectly rhyming, completely historically accurate sonnet about 18th century French history. The quantized version, it might miss a single rhyme scheme or forget a highly obscure historical date. It's slightly less sharp, but still highly capable. However, thanks to advanced quantization methods like GPT-Q, the trade-off is astonishingly in your favor. We're often looking at a massive 75% reduction in memory usage for a barely noticeable 1 or 2% drop in overall accuracy. It's an absolutely incredible bargain. You get a model that's a fraction of the size, runs blazingly fast on hardware you already own, and is almost indistinguishable in quality from the original massive version for 99% of your daily tasks.
Ultimately, this highly technical optimization technique serves a deeply human goal. As Mark Zuckerberg pointed out during Meta's recent releases, open source will ensure that more people around the world have access to the benefits and opportunities of AI. If artificial intelligence is only controlled by a few massive trillion-dollar companies, they act as gatekeepers to the future. But if these models can be compressed small enough to run on any standard computer, that power is completely decentralized. By combining open-source software with powerful quantization techniques, AI technology can be deployed much more evenly across society.
So, as these models inevitably grow from billions to literally trillions of parameters, I want to leave you to think about this. Will extreme quantization be the ultimate key to keeping artificial intelligence in the hands of the public? Without it, only massive corporations can afford to run the future. With it, the future might just fit right inside your laptop. Thanks for joining me for this explainer, and keep exploring.
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.